Okay, so imagine you have a lot of pieces, puzzle pieces, three-dimensional puzzle pieces that you are trying to assemble edge to edge to create a sphere. In other words, these pieces are parts of a shell that you would like to interlock somehow so that when they all are formed, the puzzle, of course, is to try to interlock them to create a perfect sphere. This poses a lot of challenges to just make this physically. I've been trying to make a puzzle like this for years and years. And originally I wanted to try to make the pieces all mechanical, meaning that they would just somehow physically interlock, maybe with tongues and grooves that can slide together, or maybe they have notches in them somewhere that they interlock, and so forth. But this really is very limiting. It's limiting in the shapes of the pieces that you can make. Usually they have to go completely edge to edge like this. In other words, they can't go partially from a smaller edge to a longer edge, because then you don't know exactly where to put all the notches and things like that. And it's just very hard to do, and it's very much dependent. If you have very simple symmetric pieces, then you might be able to pull it off. But then even getting them to stay together, if you want all the notches to interlock, getting the last piece in on a sphere, a piece in a sphere, it usually would not want to go in. These are all problems, if I've described them well enough, in trying to make pieces of a shell that interlock to create a whole sphere. I finally decided to try to use magnets. Now, generally I try to avoid using magnets in a puzzle. Magnets can be expensive. If the magnets break loose from the puzzle and they're swallowed, they can be very dangerous and things like this. Plus, there's something about the elegance of a purely mechanical solution, something like the Rubik's Cube, which was purely mechanical, no magnets or anything like that. But after years and years of trying to design something with just notches and grooves and tongues and grooves in a puzzle style like this and not being successful, I thought, okay, let me try to use some magnets. But even that has not been completely trivial. The main thing with magnets is they have polarities, and if you, much like the notches, depending on where you would put the magnets on the edges of the pieces, they might stick together great in one combination, but if you rotate the piece or you try to do anything unusual, then very likely you're going to have two similar polarities on magnets repelling one another, and so the pieces wouldn't, in fact, not want to go together at all. They would repel one another, which would not make a very good puzzle. So how do you get around this and the magnets? I tried several things. Here are some pieces, and on the faces I put very weak magnetic sheets. These are like photographic magnet pieces of paper you can get, and I cut it to match pretty much the edge or the face of this piece, and I have another one right here, but this does not work. I was hoping maybe the weakness of the magnet would be just enough that they would hold together, but they don't, because once again, polarity, the way this magnetic sheet works, whether you know it or not, they're only really attracted to one another if they're at roughly 90-degree angles, based on very thin grooves that you can't even see on the sheets. So let's see if I can get these to work. These pieces hold together like this, but if you turn the magnets, they don't hold together at all. So they would only hold at that very specific orientation, which again completely defeats the purpose, because I might have the piece oriented this way and need it to stick, or in other words, I wouldn't know how to fasten these pieces, and if it just wouldn't work. The polarities would not necessarily match up. You'd have about a 50-50 chance of them matching up perfectly, even if you could perfectly orient the magnetic paper on the face of the plastic piece, which is a very unlikely thing. So what after that? Well, I learned a trick from a friend, Charles Pillman, who's a friend of mine, had heard of a guy who took spherical magnets. Oh, I should say another option would be to just embed magnets into the side of the piece. So maybe 3D print depressions in the side of this and then glue the magnets in. But again, you run into the problem of once the magnets are fixed into the side, that polarity is fixed, and so you get some restrictions on which pieces could go to which. You also have the issue of glued magnets maybe wanting to pop out. I have since then learned how to finesse my 3D printer so that I can pause the 3D printer in mid-print and embed the magnets on the interior of the pieces. That way the magnets are not visible on the outside, but if they're close enough to the edge, they still have a strong enough attraction force to hold pieces together. That's great as far as the magnets popping out, but it still doesn't solve the problem of polarity. Now, an advancement, again, that my friend Charles Pillman had alerted me to. He did not come up with this himself, but he saw another engineer or industrial designer or somebody, hobbyist, come up with this. Take spherical magnets. Here are very tiny spherical magnets, and when you're 3D printing the pieces, 3D print a cavity, a spherical cavity or cylindrical cavity that is slightly bigger than the magnet. Drop it in, print over it. The magnet is now embedded inside, but more importantly, it's loose and it can rotate. So when you hold two pieces up together, and that's what I've done with this yellow and pink piece, when you hold these two pieces together, I have magnets. You won't be able to see them, but there's a magnet right here in this corner, there's a magnet in this corner, and there's a magnet in this corner. And again, they can all spin freely, so they in fact hold together. This is much more promising. They hold together here, and they hold together like this, and so forth. However, I ran into this issue then. Trying to get the geometry perfect to know exactly where to put the cavities and the holes so that the pieces will line up vertice to vertice, regardless of how you might orient the pieces. What's the issue here? Notice when I put these two pieces together, if you look right here, this corner or this vertex matches almost perfectly with this vertex. It's a little bit off, but not that bad. But notice when I put it this way, how far off the sliding is. This is the natural magnets trying to hold each other together. Now I can force it the other way, but as soon as I let go, it slides back to where it was. Maybe when you put all the pieces together, these would equal each other out, but it would not be as strong an attraction as you would want if you're forcing the magnets apart somewhat. Furthermore, what would happen if I tried to put these pieces and not perfectly edge to edge? You run the risk of the magnets just being in the wrong place, the cavities being in the wrong place. The geometry is extraordinarily tricky. It might be doable to find the perfect place to put holes in each corner of this piece so that they all hold together regardless of what orientation, but I'm very skeptical that that's possible. You also have to worry about the size of the magnets, the attraction force of the magnets. If they're too close to the edge, then they're going to be visible, or they're going to not be fully contained in the side. All of these engineering problems with this. So, what did I finally do? This was very close though. Notice again, if I maybe had tweaked where the cavities were inside, it might have worked. But this led me to the final innovation, which I believe is finally going to work. In fact, I know it does work because I've completed the puzzle at this point, which I'll show at the end of all these videos. That is this. Instead of printing a single cavity, spherical cavity in each corner in which I place a magnet with just a little bit of tolerance so that they can float around, I realized it would be good to have the cavity on the interior of the plastic piece be an actual tube or a tunnel that runs along the inside, not the whole length, but most of the length of an edge. So let's look at the blue and red pieces. I don't know if this is going to be visible. You can maybe see the detail here in the correct light. You'll see a little bit deformation from the printing. There's a whole tube here which is big enough for a round magnet, a spherical magnet, to actually move back and forth. And there's another one here, you won't be able to see it on this side, that goes about almost the whole length, not quite the whole length, and on each of the three sides. when I'm printing the pieces, I drop magnets down, one magnet into spherical magnet into each of those tubes. It prints over it, and you can hear the magnets are loose in here. Well, they actually attract one another in the corners, but what this happens is when you put two pieces next to one another, now this seems not exactly in the right position. This certainly isn't in the right position. Notice these are holding together though. But I can drag these pieces now, and the magnets move within the tunnels, and they have enough leeway to get almost any orientation or any alignment. So this piece holds together this way as well, which there's no way this would have worked with the orange or the yellow and pink pieces earlier, because those magnets were locked in relative secure positions. Now though, look here, the spherical magnets are actually dragging within their tubes, and so you can have the pieces match up nearly any edge to edge. You can't quite do a corner to corner like this because the tubes are no longer adjacent to one another, and you can actually hear the magnets moving around and sliding around and popping into place. It also works on this smaller side. These two sides match, but just as importantly, I can get a small side to match up along a longer edge, and pretty much anywhere along that longer edge, because the magnets within are moving around as they need to go. This works. So again, here I can move the pieces around. It takes a little jiggling sometimes to get the magnets to play with one another and to attract one another, but it is possible to get two pieces to come together and hold together. And like this. And you can again hear the magnets moving around as they attract one another, and this will work when all the pieces are assembled to get a sphere. Showing the final sphere build will be at the end of this series of videos. What I'm going to show next is myself actually putting in middle of a 3D print, dropping these magnets inside one of the tubes so you can actually see on the interior of one of these pieces. But this works. This is finally a solution to give you much more flexibility as far as pieces lining up, and giving you much more freedom in designing certain types of spherical, not just spherical, but any polyhedra puzzles where you're building interesting shapes from multiple pieces. Okay, that's it for this very long segment.